right, ask me a question. That's why we're here.
Why are we here?
Ask questions. You guys think of something to ask me? Hey, Zoom people, can you hear me? Give me something on the chat or just speak up.
Yeah, we can hear you.
Awesome, thank you. You guys can ask questions too, but I will have to turn your volume up. All right. No questions. Class dismissed. Just go over it.
I have a question about the cell phone one on learning how to edit.
Okay. I didn't do those, did I, in class?
I don't think so. You didn't do it in class.
There's a lot of stuff on there I didn't get to. There's just so much of it, and I just throw it out there. So, all right. So, ask me one of those. What does it say?
A cell phone without a case is dropped 4 meters on planet Earth. The phone hits the ground in 0.5 seconds. What is the acceleration of gravity on planet Earth?
So we're going to look for little g on planet X, right? So what's this information for? What are we going to do with this information? You kind of have to think back to chapter 2 or 3 to answer this question. What is g? What is g on Earth? Yeah, what does that represent? Say again? Well, but what does it represent? What does 9.8 meters per second squared represent? Okay, what does that mean? Okay, but what do you mean? What does the acceleration determine? Okay, so using this 4 meters and this 5 seconds, can we determine g? We can, right? You'd have to go back to those equations. Which equation is it? This is why I didn't do it in class, because this was just going to draw a little too much time going back to chapter 2 or 3 for this part of the equation. I could have asked the rest of it, but so how do we get little g on planet X?
Y minus y naught equals b naught g minus y half.
So y, this is this equation, right? Y equals y naught plus v naught y times t minus 1/2 g t squared, right? That was equation 4. So what is my y in this picture? What does the variable y represent? Yeah, it's the vertical position, right? This is the final, and this is the initial. So what would you call y and what would you call y naught? Struggling. What's v naught y? What does it represent? First, let's say what it is. Yeah, it's the what initial velocity? In what direction? Yeah, in the y direction, right? In the vertical direction. Yeah, that's fine. In the vertical direction. I know what you meant. So what's the initial velocity of the cell phone in the vertical direction? Why? Because you dropped it. You didn't throw it down. You just dropped it. So it left your hand. It had the same speed your hand did instantaneously, which is 0. And then it fell, right? And so if I was looking for G here, we never specified what G had to be. It could be on the moon or some other planet, right? Well, this is all happening on planet X. And so this piece is 0. And so I can say, if I rearrange this equation, I can say 1/2 G on planet X t squared is equal to y0 minus y. This gets rid of my minus signs, right? This guy is 0. We just said that's where it lands, right? And this guy is 4 meters. And so I can solve for my gx. Gx is equal to 2y0 over t squared. That's how they measured G on the moon. They could just drop something in time. But they didn't really measure it that way because they didn't actually land on the moon. We all know that. Just kidding. The way they measure G is actually, in reality, is they have a, they'll send some spacecraft out into space, and they'll fly it past the moon, and its trajectory will be curved by the pull of gravity from the moon. And they use that calculation to measure the moon's gravity and mass and stuff like that. They get all the details just by flying past it and seeing what it does to the direction of the spaceship's trajectory. And so this is 2 times 4 meters over 5 seconds squared. Is that what I said? I don't know what 8 over 25 is. 25 goes into 8. Is that 32 times? Was that a choice? I'm going with that one. Oh, it's 0.5?
Yeah.
Well, that messes me up completely. So this is 0.25, and so then that's 32.
Yeah.
Right. That's only off by a factor of 100. It's partial credit. All right, so 0.5 seconds. So what's the next question? Now it's going to ask me something that's meaty.
How fast the phone is
Oh, no, that's not meaty. That's still a chapter 2 question, right? Could we figure that out?
The one after it asks if, or it says if the planet has a radius of 8,000 kilometers, what is the mass of the planet in kilograms?
That's how you calculate how fast it was going. There's equation 2, right? And so we could say V is equal to 0 minus 32 meters per second squared times 0.5 seconds, which is 16 meters per second. That would be the velocity. And so here comes the question. Right, we said the radius of the planet. Tell me again. I'm sorry.
The radius was 8,000 kilometers, and it's asking what the mass of the planet is.
8,000 kilometers, so 8 times. So where is G in all of the what's Newton's law of universal gravitation? After you've tattooed the 5 kinematics equations, you should have the Newton's law, first law, second law, and third law. There's still room before you get to your elbow joint for the law of universal gravitation. What is it?
Is it the G constant times mass of 1 times mass 2 over Earth squared.
Yes. Right? On the surface of the Earth, this is just mass times gravity. These two are the same thing. And so this piece here is G. I think we talked about this in class one day. If you multiply these guys together, G times the mass of the Earth times the radius of the Earth squared, again, little g is 9.8 on the surface of the Earth. And so if you stick in G times the mass of the Earth or divided by the radius of the Earth squared, and 6.67 times 10 negative 11 Newton meters squared per kilogram squared times 6 times 10 to the 24th kilograms divided by 6.37 times 10 to the 6 meters quantity squared. Punch all that in your calculator. Lo and behold, you get 9.8 meters per second squared. That's what it comes out to. Well, you can evaluate that for anything, right? And so this is your G on any planet. If you put the moon's mass in there and the moon's radius, or planet X's mass in there and planet X's radius, you would get G on any of those objects. And so if I come back over here and I say, well, G on planet X is equal to big G times the mass of planet X over the radius of planet X squared, right? I know this because they just gave it to me. I've already calculated this one and I know big G, and so I can say the mass of planet X is equal to little g sub X times big G times the radius of X squared. Did I get it right? Multiply by R squared, divide by G, my bad. GX over big G, there we go. And so this is, what did I say, was it 32? Times 8 times 10 to the 6 meters over 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. What's that, 2/5, 2/3, 2/8, 256. 6. Divided by 20. It's 13. Well, I have to square this one, don't I? There we go. That's better. I don't know what that is.
3.07 times 10 to the 20.
Say it again.
3.07 times 10 to the 20.
Go with you on that. I feel like I've lost it. No, that's right. So for any planet, you can just evaluate this piece, and that's little g, at the surface of the planet. So if you know the radius of the planet, you know the mass of the planet, you can evaluate g at the planet. You know the radius of the moon, mass of the moon. Gravity on the moon is 1.67 meters per second squared. On Mars, it's like 3.5. If we inhabit Mars, people are going to have some serious basketball skills. The moon even more so. Were there any more on that? Oh, thank you. You're welcome to join us.
So, around 25 seconds. The mass is 0.2 kilograms, so it's a force of gravity on the phone.
Yeah. So how would you do that?
Multiply g times the mass.
Yeah. I think on that one, that sheet, there was one that was wrong. Who came and showed me it? I can't remember. Somebody showed me there was a mistake on one of these problems where, oh no, it's a force problem. Yeah, so the force of gravity on planet X is just mg on X. which is, what was the mass of the phone you said, Nick?
0.2.
0.2 kilograms times 32 meters per second squared is 0.64. No, 6.4.
Yeah.
So it's got like 3 times the gravity we have. So instead of weighing 200 pounds, I would weigh 600 pounds. I probably couldn't walk on planet X. It would have much stockier animals on it. Let's see why I couldn't have animals on it. All right, next question. There was one with the friction where there was an error on it. Where I said mu sub k is equal to 0.6, mu sub s is equal to 0.8. And what was the mass of that one? How many?
10.
10 kilograms. I think I said if you push with 79 newtons, what's the friction force? What is it? Say louder. 79, right? Why? What would it have to be for, which kind of friction is that? Static. Why is it? Why wouldn't it be kinetic at that point? What's the definition of the static friction force? Right? And so this has a maximum value. What's the normal force on this thing? How many?
100.
How do you know?
Yeah.
Say it again.
Mass times gravity equal to 100.
That's the weight, right? There's a normal force on it. How do we know that the normal force is 100 newtons? How do you know they're equal?
They're opposite.
They're opposite, but how do you know that they have to be the same? In which direction?
Up or down.
Up or down, right? And so I would say, I've got 2 forces acting in the vertical direction. And so I can apply Newton's second law. The sum of the forces in the y direction equals ma sub y, which is 0, because it's not moving in the y direction, right? And that says, well, look, that means that the normal force minus the force of gravity. Why do I subtract the force of gravity? Why the minus sign? Because it's pointing down. This is my coordinate system, which I didn't draw, but now I'm drawing it. Equals 0, so that the normal force is equal to the force of gravity. That's equal to mg. That's equal to 100 newtons, as we already determined. And so my normal force is 100 newtons. That's how I know the normal force. At some point, you kind of do all that, as I think you guys are doing in your head, right? At some point, you say, all right, it's not moving in the y direction. That means these 2 guys have to be equal. We say, otherwise, there'd be some kind of net force there, and there isn't. And so that means this guy is the same as this guy. I can evaluate this guy, which is just mg, it's just 10 times 10. And that means this guy's also 100. So I can plug that over here. This is 100 newtons. Sorry, 100 newtons. And so this gives me 80 newtons for my max static friction. Right? How hard do I have to push to not be dealing with static friction anymore? 81 or 80.0001 or something. 81 is a good number, right? So 79, what happens? Static friction scoffs at me, right? You do not have enough force, right? And it just pushes back with an equal force so that the object doesn't move. Static friction matches my force until I exceed it, and then the object moves and I deal with kinetic friction, right? So this is, so in this case, so the problem I was talking about, I don't know, it's 9 or 10 or something like that. I didn't even give 79 a choice, but if the push force is 79, then that means I have a static friction acting and it's just balancing whatever I do. When I push on the object and it hasn't moved yet, static friction just pushes back however hard that I push. So what happens when I push at 81? So now I'm going to change this guy, right, to 81 newtons, right? And so now I have to deal with kinetic friction. Do we all agree on that? Why? 81 exceeds this guy, right? Anytime you're doing a friction problem, if kinetic and static are involved, you probably have to check to see if your force causes the object to move by exceeding the static friction force. You almost always have to go over and look at what the maximum static friction force is, calculate that. That might mean you have to do some work to calculate the normal force, like we did a minute ago, right? And so now, so you said it's kinetic friction. So now I have kinetic friction pushing this way. What's its value? Formula-wise, what's the formula for kinetic friction? I cannot write it that way. It's perfectly okay to say Fn times mu sub k, but it totally messes up my OCD. I have to have the v first. I don't know why. So 0.6 times the same 100 newtons. We already determined that, right? That doesn't change. That's just a vertical action going on, which is 60 newtons. Right. And so this guy pushes back with a force of 60 newtons. What's the net force on the block? Right? Yeah. Okay. So that's my net force. How do I figure out what the acceleration of my block is? So now I have this, right? I can say F net equals mass times acceleration. Acceleration is equal to F net divided by the mass. That's equal to 21 newtons divided by 10 kilograms, which is 2.1 meters per second. So once I get up to 81, I've just exceeded the maximum static friction force. Now all of a sudden, I'm pushing against the kinetic friction force. And that's what happens when you're pushing on a box that all of a sudden starts to slide and you go, whoa, that was nice. Right? It all of a sudden starts to move. Get that acceleration. Right. I kind of asked that one. What else?
Those pulley problems that we get to do in class. It's learning catalytics, Newton's laws, starting at 3. So it's like we have a mass up here. It's connected to a pulley that is connected to a second mass.
Was there a homework problem like that?
No. I mean, on the study guide, yes, but not.
It wasn't in the homework? I probably won't ask you that. Normally, I would say in most semesters, I do that problem. I don't know why I didn't do it.
Talk about the forces from the books.
Yeah. What are their masses? It's like 5, 15, and 25?
Yeah.
All right. Ask a question.
What's the force on the bottom book due to the
Okay. So what are all the forces acting on the middle book? Just all of them. Who can give me one force acting? Oh, wait. On the bottom book due to the middle book.
Yes.
Let's start. What's the first question in that row? Let's start with the top one. What's
Identify all objects exerting a force on the middle book.
all right? Let's just start with that one. What are all the objects exerting a force on the middle book? Okay, so Fn. What's the object exerting the normal force on the middle book? Say again? The bottom book. Does everybody agree with that? It's the thing that's sitting under it. The thing that's exerting the normal force on my cup is my computer. Right? Now it's the table. Right? Now it's my hand. Right? It's any of those things. It's whatever's in contact with it. What else is exerting a force on the middle book? That's gravity isn't an object. The earth, right? I was being a little silly there, right? I'll just put in parentheses. Right? What else is exerting a force on the middle book? The top book. Which way is that force? Technically, that's also a normal force, isn't it? It's a contact force, right? I'm going to call it F top on middle. What's the value of that force? What's the value of this force? We know one of those, right? Do you know the normal force due to the bottom book on the middle book? Do you know this one? So let's go back to this guy. The force due to the top book on the middle book. We don't know what that is. Suppose I flip this around and said, what's the force due to the middle book on the top book? Do you know what that one is? How do you know? What's that? Well, how do you know it's 5 newtons? I mean, oh, it's because you're reading 5 newtons. What are all the forces acting on the top book? All of them.
The normal force from.
I'll just put it in red for the top book, right? What else?
And gravity Earth.
So we just did this a minute ago with the what's the problem we just did a minute ago? Oh, with the block with the friction, right? We said, hey, the normal force and the weight have to be the same because they're the only two forces acting and it's not accelerating, right? And so we know this, right? And this is 5 newtons. So what's this guy? Also 5 newtons, right? We all agree on that? What's the equal and opposite force for this guy? This is the force due to what on what? This is the force due to what on what? The middle book on the top book. What's the equal and opposite force for that? What's the Newton's third law pair for that? The top book on the middle book. What's its value? 5 newtons. Right? Does everybody get that? It's like the towers of Hanoi. You do the easiest one, and you can work your way down. Right? And so now we have this guy and this guy for the middle book. You with me? So I've got 2 forces, top on middle, and the force of gravity. This one's 5, this one's 15. What's the force due to the bottom book on the middle book? How do you know?
Because the force of the top book is acting on the middle book, and then both of those are acting on the bottom book. That's right back up.
So these 2 forces, this one and this one, are both acting on the middle book downward. But the middle book isn't moving. So there has to be an equal amount of force pushing it upward. So if I said the sum of the forces, I'll use black, right? The sum of the forces in the y direction equals ma sub y equals 0 for middle book. That leaves me with the normal force, this one, minus F top on middle, minus the force of gravity equals 0. This is Fn minus 5 newtons minus 15 newtons equals 0. Fn is equal to 20 newtons. Way back when we first started talking about Newton's laws, I said Newton's third law is often useful for figuring out a force that you don't know because the equal and opposite one is easy to figure out. And so if you keep that in mind, this is a simpler object to look at than this because this guy has pretty easy to define what the forces are acting on it. And so you can say, oh, okay, the normal force is this guy. What's the equal and opposite force for the normal force? Oh, that's this force that I wasn't sure of a second ago. And so now I have 2 of these guys I can figure out. I can determine that one. And so I think that was the question you asked me, Lauren. Am I wrong? So the force on the bottom book. Wait, what did you ask me? Oh, the force due to the bottom book on the middle book, right? And that was the normal force. Bottom book on the middle book. That's this thing. That's what calculates 20 newtons. What's the force due to the on the bottom book due to the middle book? Say it loud. 20. It's just the equal and opposite force to this one. This is the force on the middle book due to the bottom book. So the force on the bottom book due to the middle book is equal and opposite to that. It's Newton's third law pair. I do it to you, you do it back to me. And so this, the force on the bottom book due to the middle book is 20. And if you just thought about that, you'd say, yeah, it's 20 because it's having to support 20 newtons of weight. I set 20 newtons of books on top of it. And so the force that's experienced from these two guys is 20 newtons. What else? Are there more of those? The key to these problems is to just work from something simple and work outward, you know. Sometimes you can almost common sense them, like the force exerted due to the middle and the bottom. It's just you set 20 newtons on it. So it's got to push on 20 newtons. All right. What else? Yeah.
Jason pushes on Homer with forces 200 newtons, 30 degrees north of east. What's the eastward component of the force? In newtons.
He pushes in a direction. And it's pretty. Yeah. Look at that. So this is, what was the force? How many?
200.
200 newtons,
30 degrees north.
30 degrees north of east. So I'm going to say that's east. And so my force is going to be 30 degrees north. Like that. And so the question is what?
What is the eastward component of this force?
So how do I get the eastward component out of that? Cosine, right? The way I get to the components is I draw a line straight down, right, to one of the coordinate axes, in this case, north, south, east, and west, right? There's north. And so this is Fy, and this is Fx, and this is my eastward component. And so cosine of 30 degrees is adjacent over hypotenuse, which is Fx over F. And so Fx is equal to F cosine of 30 degrees, which is 200 newtons, times the cosine of 30 degrees, and that's 173 newtons or something like that. Was that a choice on there?
Yes.
So to find the northward component, it's just sines.
Yeah, it's just the sine, which is, what's the sine of 30 degrees?
Opposite.
Yeah, what's its value? What's the sine of 30 degrees? 0.5. And so it'd be 100 newtons. You don't have to know them, but. Probably if you're going to health sciences, you don't have to remember the cosines. Sines. If you're going to some technical field, you might. It's good to have them.
Question.
Yeah.
So question's asking 10 kilograms is hanging on a vertical wire. What is the tension in the wire? And it's just the mass times gravity, and so just beyond.
Is there not a right choice on there or something?
Yeah, the right choice was 10 newtons. so
Oh,
we're
I'm
just making
sorry.
sure.
Yeah, yeah. Yeah, that's what happens when you. Doing those in class, I can just edit them on the fly, but if I don't edit them, so this is 10 kilograms. That's what he's talking about, and the tension in the wire, you know, the tension is just it's just similar to a normal force, right? It's just holding the thing up, and so the force of gravity here is just mg, and that's 10 kilograms times 10 meters per second squared, which is 100 newtons. And so that tension, since the net force has to be 0, this tension has to be 100 newtons. And I said 10 newtons.
We went through the satellite questions.
Yeah.
So. Satellite mass 1,000 kilograms orbiting the Earth. I'm gonna skip to one a little farther ahead. Is that okay? Or do you want to start?
Would you give me the data? It gives you a height, right? And the height is like 6.3 times 10 to the 5th meters.
Yes. Yeah.
And then if you add the radius of the Earth, which is 6.37 times 10 to the 6 meters, you get the orbital radius of the satellite is 7 times 10 to the 6 meters.
Yes.
Is that where we're at? And then so now what do I do with that? What you can ask me any of the questions.
So what is the gravitational force acting on the satellite?
Right. Okay. So the force of gravity on the satellite. What's the formula for that? Everybody say it at the same time.
One object, mass, second object, gravitational constant divided by the radius squared.
You put the G on the end. I would just fail you for that. Yes, you said it perfectly. It's fine. 6.67 times 10 to the negative 11th meter squared per kilogram squared times 6 times 10 to the 24th kilograms times 1,000 kilograms divided by, let me try it one more time, 1000 kilograms divided by, and this is 7 times 10 to the 6 meters, all squared, right? And so if I evaluate that, I get, I think it's like 8,200. Is that right?
Yeah.
Something like that.
So then what is the approximate acceleration?
Right. And so how do we get that? It's asking, so the next question is, what is the acceleration? Right. How do we evaluate that? What's the formula for evaluating the acceleration?
Is the second equation.
Yeah, it's the sum of the forces equals the mass times the acceleration. Technically, I should have drawn a free body diagram, and I still can, right? Here's my Earth, say, right, and here's my satellite. And if I draw my satellite over here, right, then its acceleration is in this direction. How do I know its acceleration is in that direction? Yeah, I've got a centripetal force acting on it, and it's always towards the center of the circle. I cleverly draw my coordinate system, so that's in like the plus x direction. If I put it up here, it would be in the minus y direction, and that's not much more difficult, but now I've got a minus sign to deal with. So I always put my satellites over here on the left side so that I can draw my little coordinate system like this, and my acceleration is in the x direction, right? And I've only got one force acting. What's the force acting? So it's really easy. Sum of the forces is just this thing. It's the force of gravity is equal to mass times the acceleration. The acceleration is equal to the force of gravity divided by the mass. And that's 8,200 newtons divided by 1,000 kilograms, which is 8.2 meters per second squared.
Question, Dr. Trent. So for like the arbitrary values of like the radius of the earth and how much the earth weighs, will we be given that, or is it like,
You have to memorize those.
all right?
I'm just kidding. No, I'll give you those. I think they're on the sheet, aren't they?
Yeah.
They should be on the sheet. Yeah. I think I told you I had a student in my physics class about 10 years ago who hated sheets. He wasn't in this physics class, he was in a majors class. And so he would memorize everything. He memorized all the equations, all the numbers, any formulas, any constants. Are you sure you don't want that sheet? Sheets. I want it all in my brain. That's pretty hardcore. But that's the guy you want operating on you, right? That's the guy you want cutting you open.
Can we do the next satellite question solving for speed? of satellite?
Yeah, so how do we get the speed of the satellite? From the things we know, where does the speed of the satellite show up? How could you get a V in here somehow?
FC equals squared by R.
Yeah. The acceleration here is a centripetal acceleration. And so A sub C is V squared over R. That's where the V comes in, right? And so I get V squared is equal to R times the centripetal acceleration, or V is equal to the square root of the radius of the orbit times the acceleration. I come all the way back over here, I get V is equal to the square root of 7 times 10 to the 6th times 8.2. It's a square root of 50, so it's going to be like 7.6 times 10 to the 3rd.
Yeah.
See what I did there? Square root of 10 to the 6th, 10 to the 3rd. Square root of the product of those two is going to be somewhere in between them. Just took a shot at it. Meters per second. Technically, this is meters, and this is meters per second squared. If I was doing what I should be doing. Which is back to about 5 miles a second. Just what?
What's the time in seconds that it takes for the satellite to orbit the Earth?
So how would you figure that out? Well, what's the path it's following? What's the length of that path?
7.0 times 6.
7.0 times, so
Would it be the radius or would it be the diameter?
what's the shape of the path it's following? It's a circle. How is the length of a circle related to the radius of the diameter? I'm going to go get all of your 12-year-old siblings to come in and tell you how the radius of a circle is related to its circumference. Yes, it is. Right? So the circumference is 2 pi r. That's the path it's following. Right? And so the speed is just the distance over the time. It's traveling at a constant speed. Right? And so the time is the distance over the velocity or the speed, which is 2 pi times 7 times 10 to the 6 meters divided by, what did we get? 7, 6 times 10 to the 3rd meters per second. So, well, that divided by that is 1,000. So it's times 1,000. This is like 44 divided by 7.6, let's say 7? 7,000 seconds? Is that a choice?
No.
Dang it.
Wait, 7,000 seconds? It's 7,600. My bad. Okay, no.
What are the choices?
58, 44, 3600,
So it's 58, you said?
5800.
That doesn't seem right.
630,000 meters. Up there.
Is it, am I crazy here? What do you get for the, when you calculate this, what do you get? Close to 7,000, right?
5,787.
What am I doing wrong? Oh, I see. 5,800. It's because I can't do that. 5,800. Yeah, I get it.
And then you can drive it up to here.
I've done these things 1,000 times. All right. So that's the issue. I lost my. Was that all of them? What else? What's that? How many? 20.
So we use 10 for gravity.
And use 10 for gravity. They'll say it in the instructions. And I've got no advice. I had a professor who used to say, know everything and don't make any mistakes. It's not very helpful. So, I can hang around if you guys have more questions. Everybody looks like they're packing up. Strawberry. It's like strawberry. Mango or something.
Yeah, something crazy.
Something crazy.
Spring breaker.
It's very attractive. All right, so, all right, you guys, I guess we're done. So I am going to, I'm going to put this up on, I'll put a link to this somewhere in case you want to look at it again.